Hi, my name is JD Quigley. I'm a postdoc at Cornell, and I'm applying for tenure track and postdoc positions this fall. In this video, I'm going to tell you about my work in stable homotopy theory and its connections with algebra, topology, and geometry. For most of the video, I'm going to focus on my recent joint work with William Balderrama and Dominic Culver on the Hopf invariant 1 problem in Motivic homotopy theory. At the end of the video, I'll quickly skim through some of my other projects and end with some further information about me. Classically, the Hopf invariant is defined as follows. Given a map between a 2n-1 dimensional sphere and an n-dimensional sphere, we can consider the cohomology with integral coefficients of its mapping cone, denoted C sub f. This integral cohomology is a z in dimension n and a z in dimension 2n, and we'll call alpha and beta the generators of those groups. The Hopf invariant of f, denoted hi of f, is the unique up to a sign integer such that alpha cup alpha is equal to the Hopf invariant of f times beta. Let's see an example. The first Hopf map is a map from a 3-sphere to a 2-sphere, which is given by taking the sphere in C2, which is a model for a 3-sphere, and projecting onto CP1, which is homeomorphic to the 2-sphere. It turns out that this map has Hopf invariant 1. There are other Hopf invariant 1 maps called nu and sigma in the dimensions shown below, and both of these also have Hopf invariant 1. It turns out that the Hopf invariant is closely connected to phenomena in algebra, geometry, and topology. I'd invite you to pause the video right now and look at this figure, which I've taken from Adams' 1960 paper on the non-existence of elements of Hopf invariant 1, just to see the connections between Hopf invariant 1 elements, H-space structures on spheres, parallelizable structures on spheres, and normed algebra structures on Euclidean spaces. The Hopf invariant can be accessed using stable homotopy theory, even though it's a priori an unstable object. So I really like this figure because it connects stable homotopy theory to somewhat more down-to-earth problems in topology, algebra, and geometry. In the paper that the previous diagram was taken from, Adams proves the following remarkable result. He shows, using stable homotopy theory, that there's an element of Hopf invariant 1 in the 2n minus first homotopy group of the n-sphere only if n is equal to 2, 4, or 8. What this means is that H-space structures, parallelizable smooth structures, and division algebra structures are extremely rare. Balderrama, Culver, and I are interested in understanding the same type of question, but for varieties instead of topological spaces. For this, we need Motivic homotopy theory, or the homotopy theory of algebraic varieties. Let's fix a field K. A motivic space over K is a simplicial presheaf on the Nisnevich site of smooth K schemes. This definition is a little too technical for this video, so for now, all you need to know is that a motivic space assigns to every smooth scheme X some simplicial set or space. With this definition, we can see that there are two different circles that we might care about. One, called S10, sends every smooth scheme to the simplicial circle. The second, S11, sends every smooth scheme X to maps from X into the multiplicative group scheme. With these two notions of circles, we can define bigraded spheres by smashing them together in an appropriate way, and we can define bigraded homotopy groups by taking homotopy classes of maps out of those bigraded spheres. Here, homotopy classes of maps, or homotopies, are understood to use the affine line instead of the unit interval. Let's see an example. The classical Hopf invariant 1 element eta has a motivic analog given by taking A2 minus the origin and projecting onto P1. These are models for certain motivic spheres, and you'll notice that the first coordinate, 3 and 2, is exactly the same as in the ordinary classical Hopf map. The 2 and 1 are just keeping track of how much algebraic information is encoded in this map. You can use motivic cohomology with integral coefficients to define a motivic Hopf invariant And you can show that the Hopf invariant of this map eta is 1, just like in the classical setting. Our first main theorem is that if the m-1, n sphere is an H-space, then there exists an element of Hopf invariant 1 in a particular Motivic homotopy group. This is a Motivic analog of the result from Adams' paper that I discussed before. This theorem has a more down-to-earth corollary. If we suppose that there's not an element of Hopf invariant 1 in that particular homotopy group, and further, if we suppose that Sm-1n is represented by an affine scheme, say spec of R, then that scheme doesn't admit a unital product. In particular, it's not a group scheme, and its coordinate ring R does not admit a co-unital coproduct. We use this theorem and corollary in conjunction with the following non-existence results. First, we showed that if K is algebraically closed, then there exists an element of Hopf invariant 1 in that Motivic homotopy group only if m is equal to 2, 4, or 8. This is a Motivic analog of Adams' non-existence result.
We do a similar analysis over other base fields, but in these cases, we obtain looser restrictions on when there exists an element of Hopf invariant 1.
For those familiar with the classical Hopf invariant 1 proof using the Adams spectral sequence, I've included a technical theorem, which is how Balderrama, Culver, and I prove this. So what we really do is compute all of the D2 differentials out of the one line of the Motivic Adams spectral sequence over each of the base fields above. To prove this technical theorem, we introduce the Motivic lambda algebra, which is a Motivic analog of the lambda algebra used, for instance, in the 1980s and 1990s to make a lot of computations in stable homotopy theory. Those computations suggest several future directions for this work. For instance, our connections between algebraic geometry and Adams differentials suggest that it might be possible to show that certain elements in the Motivic Adams spectral sequence are permanent cycles by producing unital products of solvent varieties. Another direction, following Tangora's work in the 80s, is to try to use the Motivic lambda algebra to compute the E2 term of the R-Motivic Adams spectral sequence in a large range. A third direction is constructing Motivic Brown-Gittler spectra. These were constructed using the classical lambda algebra in the 70s, and they were used in a variety of applications, including the Siegel conjecture, the Sullivan conjecture, and certain problems in chromatic homotopy theory. Finally, there's an interesting family of elements that we produce in the R-Motivic Adams 3 term, which have the same dimension as a famous family of elements in the classical stable stems called Mahold's eta J family. So one other future goal is to reconstruct this family just using R-Motivic homotopy theory.
Okay, that's all I wanted to say about the Motivic Hopf invariant in this video. I think this project really captures the main theme in my research, which is extending classical stable homotopy theory to the Motivic setting, or, as you can see from the slides playing now, equivariant setting, to prove new results in algebra, topology, and geometry. If you are interested in hearing more about my work, or just chatting about related math, please feel free to send me an email or check out my website listed here. Thank you for your attention.